Out there in the silent velvet darkness hangs a question. It is a query whispered not in words, but in the upward tilt of a human head, in the focused lens of a telescope, in the launch of every hopeful rocket. It is the most profound and persistent question we have ever asked ourselves. Are we alone? For millennia, this inquiry was the domain of philosophers and poets, a gentle wandering beneath a canopy of impenetrable celestial jewels. We painted our gods in the constellations and saw our myths reflected in the void. The stars were a beautiful but distant backdrop to the singular drama of life on Earth. We believed, with an almost religious certainty, that this blue marble was unique, a solitary miracle of warmth and water in an infinitely cold and sterile cosmos. But in the last few decades, a revolution has quietly reshaped our understanding. The impenetrable backdrop has begun to reveal its secrets. We have learned that the universe is not an empty stage but a crowded theatre. Our galaxy, the Milky Way, is teeming with other worlds, other suns, countless orbs of rock and gas, each tracing its own silent ballet around a parent star. These are the exoplanets, and their discovery has transformed the cosmos from a place of lonely splendour into a landscape of infinite possibility. Our instruments, extensions of our own insatiable curiosity, have become our eyes in the deep. They stare, unblinking, into the stellar sea, searching for the faintest of clues. They are hunting for something specific, a reflection of ourselves, a world that is not too hot nor too cold, a planet orbiting a star not too violent nor too dim. We seek a celestial echo, a place that followed the same recipe that gave rise to us, a second Genesis. In 2015, after years of patient observation, one of our most ambitious sentinels sent back a signal that quickened the pulse of astronomers around the globe. It was a message from across an almost unimaginable gulf of space and time, a faint whisper from a distant star system hinting at a world that felt hauntingly familiar. It orbits a sun much like our own. It has a year that is almost identical in length to ours. It exists within that precious, life-sustaining sliver of space we call the habitable zone. This is the story of that world, a place 1,400 light-years away in the constellation of Cygnus, a destination we cannot yet reach, but a world we can begin to explore with the power of science and imagination. This is the chronicle of a journey to Kepler 452B, the most Earth-like planet ever discovered, our older, larger celestial cousin. Our story does not begin with the planet itself, but with the remarkable machine that found it. The Kepler Space Telescope was not merely a piece of hardware, it was a monument to hope. Launched in 2009, its mission was one of breathtaking ambition and statistical patience. It was designed to do one thing, and to do it better than any instrument ever built, to find planets, specifically Earth-sized planets, in the habitable zones of other stars. Kepler's method was elegant in its simplicity, yet staggering in its technical challenge. It did not see these distant worlds directly. Instead, it watched for their shadows. Imagine standing miles away from a colossal, blindingly brilliant searchlight. Now, imagine a single, tiny moth flying across the face of that distant beam. From your vantage point, you would not see the moth itself, but for a fleeting moment the light's intensity would dip by an infinitesimal, almost imperceptible amount. If you saw that dip happen again and again at perfectly regular intervals, you could deduce the presence of the moth. You could calculate how long it takes to circle the light, and from that, its distance from the powerful bulb. You could even estimate its size based on how much light it blocked. This is the transit method. The Kepler Space Telescope was our unblinking eye, and the distant stars were the searchlights. For 4 years it fixed its gaze upon a single patch of sky, a field in the constellation Cygnus. It was a section of the cosmos that appeared empty to the naked eye, yet it contained over 150,000 target stars. Kepler stared at them all simultaneously, without ever looking away. It was a cosmic census taker of unprecedented scale. Its photometer, a sophisticated digital camera with 95 megapixels, measured the brightness of every one of those stars once every 30 minutes. It was looking for that telltale dip, a dimming of just a few parts per million. A change in brightness so small it is equivalent to noticing a flea crawling across a car's headlight from 100 miles away. The data that poured back to Earth from Kepler was a torrent, a deluge of stellar information. It was a blizzard of numbers that required teams of scientists and powerful computer algorithms to sift through. They were searching for a pattern, a repeating periodic signal in the noise of the universe. For every genuine planetary transit, there were 1,000 false positives. Stars naturally flicker and pulse. Sometimes two stars orbit each other, creating an eclipse that mimics a planet. The team had to be meticulous, cross-referencing, validating, and scrutinizing every candidate. It was a painstaking process, a slow-motion treasure hunt through an astronomical haystack. Then, in the data from a Sun-like star designated KIC 8311864, a pattern began to emerge. A tiny recurring dip in starlight, just as the theory predicted. The dip was minuscule, indicating a small object. And it repeated like clockwork every 385 days. This was not the signature of a gas giant, a hot Jupiter orbiting its star in a matter of hours. This was different. The long orbital period immediately told the scientists two crucial things. First, that the object was far from its star, and second, that this discovery would require immense patience to confirm. 3 transits are the gold standard for confirmation to ensure the pattern is real. For a planet with a 385-day year, this meant observing it for over 3 years. It was a long, quiet vigil, waiting for a shadow to cross a star 1,000 trillion miles away. As the second and then the third transit were confirmed, the excitement grew. The star itself, now named Kepler 452, was the key. It was a G-type main sequence star, the very same classification as our own Sun. This was profoundly significant. Stars are the engines of their solar systems, dictating the conditions for any world in their orbit. A star that is too large and hot will burn out quickly, snuffing out any chance for complex life to evolve. A star that is too small and dim, like a red dwarf, may not provide enough energy, and they are often prone to violent flares that could sterilize any nearby planets. But a G-type star, like our Sun, and like Kepler 452, is a beacon of stability. It burns with a steady, enduring light for billions of years, providing the long, stable runway that the slow, methodical process of evolution appears to require. The data was in. A planet, roughly 1.5 times the size of Earth, was orbiting a Sun-like star with a year lasting 385 days, and its orbit placed it squarely, tantalizingly, within the star's habitable zone, the habitable zone. It is a concept we often hear, sometimes called the Goldilocks zone. But what does it truly mean? It is not about the planet itself, but about its relationship with its star. Imagine a vast cosmic campfire burning in the blackness of space. A planet that huddles too close to the flames will be scorched. Any water on its surface would boil away, creating a thick, crushing atmosphere, a runaway greenhouse effect that turns the world into a furnace. This is Venus. A planet that wanders too far from the fire will be frozen. Its water will be locked into a permanent sheet of ice, its atmosphere frozen to the ground. A desolate, frigid wasteland. This is Mars. But in between these two extremes there is a delicate, narrow band of warmth. A region of space where the energy from the star is just right. Not too hot, not too cold. In this zone it is possible for liquid water to exist on a planet's surface. And liquid water, as far as we know, is the essential solvent for life. It is the medium in which the complex chemistry of biology can flourish. Kepler 452b orbits its star within this precious life-giving ring. It receives only about 10% more energy from its parent star than Earth does from the Sun. The conditions, in theory, are just right for oceans, for lakes, for rivers. The announcement in July of 2015 sent a ripple of wonder through the world. Headlines proclaimed the discovery of Earth 2.0 and Earth's older cousin. But behind the excitement lay a far more complex and nuanced picture. Kepler 452b is not Earth's twin. It is something else. Something older and grander. and its very nature forces us to confront the deep cosmic march of time. Let us begin our journey to this world not with a spaceship, but with our imagination, guided by the laws of physics. We must first understand the differences, which are as profound as the similarities. The planet is about 60% larger in diameter than Earth. While its mass has not been measured directly, models suggest it could be up to 5 times that of our home world. This places Kepler 452B firmly in a class of planets known as super-Earths. We have no such world in our own solar system, so we are entering uncharted territory. What would it be like to stand on the surface of such a world? The first thing you might notice is the pull of gravity. It would likely be twice as strong as what we experience on Earth. Every step would be a conscious effort. A simple fall could result in serious injury. This crushing gravity would shape everything. Any life that evolved here would need to be robust, with powerful skeletons and circulatory systems. Trees, if they existed, might grow low and sprawling, their trunks thick and strong to resist the immense pull. Flying creatures would be a true evolutionary marvel, requiring incredible power and lightweight frames to achieve liftoff in the dense air and heavy gravity. The geology of a super-Earth would be spectacular and violent. The planet's larger mass means its interior would retain more heat from its formation. This internal engine would drive rampant tectonic activity. Volcanoes would be colossal, far larger than any on Earth, constantly reshaping the landscape. Mountains would be pushed to staggering heights, their peaks scraping the upper atmosphere. Earthquakes would be powerful, continuous events, the very ground a shifting, groaning beast. This world would feel intensely, frighteningly alive. But the most significant difference between our world and Kepler 452b is not one of size, but of age. Its star, Kepler 452, is 6 billion years old. That is 1.5 billion years older than our Sun. This is a staggering amount of time, a deep chasm of cosmic history separating the two systems. When our own solar system was just coalescing from a cloud of gas and dust, the system of Kepler 452 was already ancient. When the first primitive life was stirring in the oceans of Earth, Kepler 452b had already experienced a stretch of time longer than the entire history of life on our planet. This vast age difference is a double-edged sword. On one hand, it provides an incredible window of opportunity. 1.5 billion extra years for life to arise, to evolve, to diversify, to develop intelligence, to build civilizations, perhaps even to transcend its planetary cradle. The sheer possibility is intoxicating. We could be looking at a world that is not just habitable, but inhabited, and not just by simple microbes, but by creatures of a complexity we can barely fathom. The ruins of ancient cities could lie buried beneath its soil. Its deep oceans could hide leviathans that have swum its currents for eons. Perhaps intelligence there took a different path, a collective consciousness in a global forest, or a crystalline life form in the planet's deep crust. However, the star's advanced age also casts a long and ominous shadow. Stars are not static, they evolve. As a G-type star like our Sun ages, it grows hotter and more luminous. Over its 6 billion year lifespan, Kepler 452 has increased in brightness by about 20%. This means its habitable zone has been slowly migrating outwards. A planet that was once comfortably in the centre of that zone might now find itself on the inner, searing edge. Kepler 452b is likely receiving significantly more stellar radiation now than Earth does. This brings forth the terrifying spectre of the runaway greenhouse effect. Imagine this world in its youth. 4 billion years ago. It may well have been a paradise, a true Earth 2.0 with sprawling oceans and temperate continents. But as its sun grew hotter, its oceans would have begun to evaporate at an accelerated rate. Water vapour is a powerful greenhouse gas. More vapour in the atmosphere traps more heat, which causes more water to evaporate. It is a vicious, self-reinforcing cycle. The planet's temperature would climb relentlessly. Eventually, the oceans would boil away entirely, leaving behind a thick, suffocating atmosphere of steam and carbon dioxide, pressing down on a scorched, barren surface. The world would become a planetary sauna, its surface temperature hot enough to melt lead, it would transform into another Venus. So when we look at Kepler 452b, we are faced with two profound and competing possibilities. Are we seeing a glimpse of Earth's potential future? A warning of what our own planet will become in 1 billion years as our sun continues to age and brighten? Are we gazing upon a planetary tomb, a ghost of a once vibrant world, its life story already over? Or has life on Kepler 452b been resilient? Perhaps it adapted to the increasing heat. Maybe it migrated to the cooler polar regions, or retreated deep underground, or into the oceans. Or perhaps, in a feat of planetary engineering far beyond our own capabilities, an advanced civilization there learned to control their own climate, to shield their world from their aging, intensifying sun. The view from the surface, if we could stand there today, would be alien yet strangely familiar. Because the planet is likely tidally locked, or in a slow rotation, the days could be weeks long, the sky would not be blue, a thicker atmosphere and the light of a slightly older, more yellow star would likely paint the heavens in permanent hues of orange, amber and gold. Clouds, thick with water vapour, would perpetually shroud the sky, creating a diffuse, hazy light. The sun, Kepler 452, would appear roughly the same size as our sun in the sky, but its glare would be more intense, a fiercer, more powerful presence. The air would feel heavy, humid, and thick in the lungs. The landscape, sculpted by higher gravity and more active geology, would be one of extremes. Immense flat plains of volcanic rock stretching to the horizon, broken by mountain ranges that would dwarf the Himalayas. If oceans remain, they would be vast and stormy, whipped into a frenzy by the thick atmosphere and the powerful forces of a larger world. This vision, as compelling as it is built on a foundation of data and educated guesswork. We have never seen this world. We have only seen its shadow. The chasm that separates us from Kepler 452b is not one of understanding, but of physical distance. It is 1,400 light-years away. It is a number so vast that it defies human intuition. A light-year is the distance light travels in a single year. Light, the fastest thing in the universe, moves at an astonishing 186,000 miles per second. To put that into perspective, a beam of light can circle the Earth 7.5 times in a single second. 1 light-year is nearly 6 trillion miles. Our destination, Kepler 452b, is 1,400 times that distance. The light that the Kepler telescope captured from its star began its journey to us 1,400 years ago. It left its home system around the year 600 AD. While it was travelling through the void, the Roman Empire had fallen, the Tang dynasty was flourishing in China, the Prophet Muhammad was walking the earth. Entire civilizations have risen and fallen on our world in the time it took for that light to reach our telescope. We are seeing the planet as it was in the distant past. To contemplate a physical journey, there is to confront the true scale of the cosmos and the current limits of our technology. Let's consider our fastest spacecraft, the Parker Solar Probe. At its top speed, it travels at over 430,000 miles per hour. An incredible velocity, fast enough to travel from New York to Los Angeles in under 20 seconds, but space is vast. Even at that blistering pace, it would take the Parker Solar Probe approximately 2.1 million years to reach Kepler 452b, a journey so long that our own species might not even exist by the time it arrived. Our chemical rockets, the workhorses of the space age, are simply no match for the interstellar void. They are like trying to cross the Pacific Ocean in a rowboat. To ever bridge such a gap, we would need a revolution in physics, a complete rethinking of propulsion. Scientists and dreamers are already working on the concepts. Fusion rockets, harnessing the same power that fuels the stars themselves, could potentially accelerate a craft to a significant fraction of the speed of light. This would cut the journey time down from millions of years to tens of thousands of years. Still far too long for a human crew, but perhaps feasible for a robotic probe. Others look to the light itself for power. Enormous solar sails, kilometers wide but thinner than a human hair, could be pushed by the pressure of sunlight or by powerful lasers based on Earth. Slowly, gently, these sails would accelerate a tiny nanocraft to 20% of the speed of light. At that speed, the journey to Kepler 452b would take around 7,000 years. These are the realistic dreams. Beyond them lies the realm of theoretical physics, of science fiction. The Alcubierre drive, a concept born from Einstein's theory of general relativity, proposes not to travel through space, but to warp space itself. It would compress the fabric of space-time in front of a ship and expand it behind, creating a warp bubble that could, in theory, travel faster than light without violating any physical laws. It remains a purely mathematical concept, requiring exotic forms of matter and energy that we do not know how to create. But it represents the ultimate hope that one day the stars might not be distant points of light, but accessible destinations. For now, however, Kepler 452b remains beyond our physical grasp. It is a world we can only visit with our minds and our instruments. And even those instruments are evolving. The Kepler Space Telescope has since been retired, its mission complete. It fundamentally changed our view of the cosmos, revealing that virtually every star in the sky likely has planets. It showed us that small, rocky worlds in habitable zones are not a rarity, but a cosmic probability. It gave us thousands of candidates, a catalogue of potential new worlds to study. Now, a new generation of telescopes is taking up the search with far more powerful capabilities. The James Webb Space Telescope, with its immense golden mirror, can do something Kepler could not. It can study the atmospheres of these distant worlds. As a planet transits its star, a tiny fraction of the starlight passes through its atmosphere. By capturing that light and breaking it down into its constituent colours, a technique called spectroscopy, the Webb telescope can look for the chemical fingerprints of different gases. It can search for water vapour, for methane, for oxygen. These are biosignatures, gases that on Earth are overwhelmingly produced by living organisms. Finding them in the atmosphere of a distant world would be the most profound discovery in human history. It would be the moment we finally know the answer to that ancient question. The moment we realise that the spark of life is not unique to this world. Kepler 452b is likely too far, and its star too faint for even the mighty James Webb to get a clear atmospheric reading. But the principles Kepler taught us are now guiding the search closer to home. Telescopes are scanning the nearest stars, looking for Earth-like worlds in our own cosmic neighbourhood. Worlds we might one day be able to study in exquisite detail, and perhaps, in the distant future, even send probes to. In the end, the story of Kepler 452b is not just about a single, distant planet. It is the story of a mirror held up to ourselves and our world. Its existence proves that the ingredients that made Earth are not unique. The universe is rich with the potential for life. Its great age reminds us of the vast cosmic timescales, dwarfing our brief moment on this planet. It challenges us to think about the long-term future of life, both on our world and potentially on others. Will we be a fleeting phenomenon, or can we become as enduring as the stars? The search for another Earth is in many ways a search for ourselves. It is an expression of our deepest instinct to explore, to understand and to connect. We look to the stars for a reflection, for a sign that the universe is not a cold, empty void, but a vast, living tapestry of which we are just one thread. Kepler 452b remains a tantalizing enigma, a world of magnificent possibilities, a silent testament to the fact that somewhere, orbiting a distant sun, there may be another shore, waiting. The journey is just beginning. What does it sound like to be truly and utterly alone? Is it the roaring silence of the perfect vacuum, a quiet so profound it is a presence in itself? Or is it something else? A faint, almost imperceptible hum carried on the edge of physics, a vibration that tells a story across an impossible gulf of time and distance. Right now, a message is crossing that gulf. It travels at the universal speed limit, a ghost of electricity and magnetism, so faint it barely registers above the background hiss of the cosmos. 23 light hours it has journeyed, a marathon runner of radio waves that has sprinted for an entire day and night just to reach us. Its power upon arrival is astonishingly small, less than a billionth of a watt, a single snowflake's worth of energy landing in a global blizzard of cosmic and terrestrial noise. To even hear it is a miracle of engineering, like trying to pick out a single whispered word from across a continent. For 47 years, this whisper has been speaking to us, its voice growing ever fainter, its origin point receding ever further into the star-dusted black. This is not a signal from some alien intelligence, at least not yet. This is a voice of our own, making a call home from humanity's most audacious, most distant, most lonely creation. This is the voice of Voyager 1. It is an echo from a forgotten world. The year of its birth. 1977 was a time when the first Star Wars ignited our imaginations, when home computers were a fantasy for all but a handful of hobbyists, when the digital world we now inhabit was the stuff of science fiction. From that distant technological past, we flung a 3/4-ton machine of aluminum, gold and plutonium into the great unknown, a marvel of slide rules and analog genius. Its central computer, the brain of this intrepid explorer, has less processing power than the key fob you use to unlock your car. Its memory is measured in kilobytes, not gigabytes, a digital capacity so minuscule it could barely hold a single low-resolution photograph today. And yet this relic, this masterpiece of antique electronics, continues to function, to explore and to report back from a place no human-made object has ever been before. It was never designed for this. The mission's original architects dreamed of a 4-year tour of the gas giants, a brief but brilliant flash of discovery that would rewrite our textbooks on the outer planets. They built it to survive the savage radiation belts of Jupiter, to withstand the cryogenic cold of deep space. But they never truly dared to imagine that nearly half a century later, its nuclear heart would still be beating its instruments, still tasting the void, its antenna still faithfully pointed toward a tiny blue dot it can no longer even see. The engineers who built it are now retired, some have passed into history, yet their creation sails on a testament to a time when we dared to build things that would outlast ourselves. It is a monument in motion, a pyramid for the interstellar age, carrying a message not for the gods, but for the cosmos itself. Strapped to its side, a golden phonograph record, a gleaming time capsule containing the sights and sounds of our world. The greetings in 55 languages, the murmur of the wind, the cry of a newborn baby, the soaring concertos of Bach and Beethoven. It was a gesture of monumental optimism, a belief that even if our civilization fades, something of our spirit, our art, our curiosity might persist. It was a message in a bottle cast not upon a terrestrial ocean, but into the cosmic sea, a gesture of hope addressed to whom it may concern. But the Golden Record's true audience was never some far-off alien race. Its true audience was us. It was a mirror held up to humanity, a challenge forcing us to decide what was most beautiful, most important, most essential about our existence. What single artifact could possibly speak for all of us? The record is a profound statement about what we value, and Voyager 1 is the messenger tasked with carrying that statement into eternity. Its primary journey was one of exquisite celestial mechanics, a once-in-176-year alignment of the outer planets that allowed for a cosmic game of leapfrog. Using a technique we call a gravity assist, Voyager didn't just visit these worlds, it danced with them. It fell toward the colossal gravity of Jupiter, stealing a sliver of the giant's orbital energy, a gravitational slingshot that bent its trajectory and accelerated it toward its next target. At Jupiter, it unveiled a world of staggering complexity and violence, a planet with lightning superbolts, volcanic moons spewing sulfur, and a great red spot revealed not as a placid stain, but as a storm, more powerful than 1,000 terrestrial hurricanes. It was a revelation, a portrait of a king of worlds that transformed our understanding of planetary science overnight. Then it flew onward to Saturn, the jewel of the solar system. Before Voyager, we saw the rings as serene, solid bands of light. Voyager's cameras revealed the truth, a system of breathtaking intricacy, composed of thousands upon thousands of individual ringlets, braided, warped and sculpted by the gravitational tug-of-war of tiny shepherd moons. It was a cosmic ballet of ice and rock, a dynamic and chaotic system of unimaginable beauty. After this stunning encore performance, its sister craft Voyager 2 would continue the grand tour to Uranus and Neptune, but Voyager 1's trajectory was bent upward out of the ecliptic plane, the flat disk where the planets orbit the Sun. Its new destination was far more profound, far more abstract. Its destination was out. For decades it sailed through an increasingly empty space, a region we call the outer heliosphere. Here the solar system truly begins to dissolve. The planets are gone, the asteroids are gone. The comets of the Kuiper belt are few and far between. The only meaningful presence here is the unceasing wind of charged particles blowing from our Sun. This is the solar wind, a bubble of plasma inflated by our star's nuclear furnace that envelops and protects our entire solar system. For billions of miles, this bubble was Voyager's entire universe. It was the water in which it swam, the medium that defined its reality. Everything it had ever known, from the light of its home star to the magnetic fields that guided its journey, was a product of the Sun. But it was approaching the edge of that bubble. It was nearing the invisible shoreline of the interstellar ocean. Scientists called this boundary the heliopause. It was a place we had only ever modelled in our supercomputers, a theoretical frontier where the Sun's influence finally wanes, pushed back by the collective breath of millions of other stars, the tenuous gas and dust that fills the void between them. What would this boundary look like? Would it be a clean, sharp line, a cosmic shore you could cross in an instant? Or would it be a turbulent, frothy surf, a chaotic mixing zone of solar and interstellar material no one knew for certain? Theorists placed their bets, models were refined, but only Voyager could give us the answer. It was flying blind into the greatest unknown in human history. We, its creators, could only listen and wait as our emissary approached the waterfall at the end of the solar system. In 2004, it crossed the first of these theoretical boundaries, the termination shock, where the solar wind abruptly slows down as it begins to press against the interstellar medium. The data confirmed it. The probe had entered a strange new region, the heliosheath, a kind of purgatory between the familiar solar system and the true void. For years it travelled through this turbulent zone, a place where the Sun's magnetic field lines became compressed and chaotic. The tension was palpable in the mission control rooms. Every new packet of data was scrutinised for the telltale signs, the definitive proof that it had finally broken through. The particle counts changed, the magnetic fields shifted, but the final unambiguous confirmation remained elusive. The crossing wasn't clean. It was messy, confusing and surprising. The universe, it seemed, was far more creative than our models had predicted. Then in 2012, something extraordinary happened. The instruments measuring charged particles originating from within our solar system saw their numbers plummet as if a switch had been thrown. Simultaneously, the sensors detecting high-energy cosmic rays from deep space saw their measurements spike dramatically. It was a profound shift, a fundamental change in the environment around the spacecraft. Voyager was no longer being bathed primarily by the Sun's particles. It was now being bombarded by particles from other stars, from ancient supernovae, just from the vast galactic ecosystem. Yet the magnetic field data was still puzzling. It hadn't changed direction as models predicted it should upon entering interstellar space. Had it crossed, or was it in some bizarre, previously unknown magnetic tunnel connecting our solar system to the galaxy beyond? The debate raged for months. The data was tantalizing, but not yet conclusive. The universe was guarding its secrets closely. The final beautiful confirmation came not from a steady measurement, but from a stroke of cosmic luck. Our Sun, nearly 14 billion miles away, unleashed a massive coronal mass ejection, a solar eruption that sent a shockwave of plasma racing out through the solar system. More than a year later, this tsunami wave, now weakened and diffused, washed over Voyager 1. The effect was electrifying. The wave caused the interstellar plasma around the spacecraft to vibrate, to oscillate, to sing. Voyager's plasma wave instrument recorded the tone of this vibration. It was a faint rising whistle, a note played on the very fabric of space. From the pitch of that tone, scientists could calculate the density of the plasma Voyager was flying through. The number was undeniable. It was 40 times denser than anything encountered in the heliosheath. This was not the Sun's rarefied breath. This was the thick, rich medium of interstellar space. The sound was the proof. Voyager 1 was no longer in the solar system. The date of its arrival was retroactively calculated, August 25th, 2012. On that day, without fanfare, without a welcoming committee, a machine built by human hands silently slipped the gravitational bonds of its home star and became the first object of our species to enter the realm of the stars. It had crossed the threshold. It had left home forever. Think about what that truly means. For the entirety of human existence, our story has been a solar system story. Our myths, our gods, our science, our biology, all are inextricably tied to the sun and its family of planets. Every atom in our bodies was forged in the heart of our star or an earlier one. Every tick of our internal clocks is set by the spin of our world. We are creatures of the sun. Our home is this bubble, this sheltered harbour carved out of the galaxy by the solar wind. Until now, nothing of us had ever existed beyond that protective sphere. But that is no longer true. A tiny piece of humanity, a 47-year-old plutonium-powered robot, is now a citizen of the Milky Way galaxy. It breathes the air of other stars. It feels the winds that blow between worlds. It is an extension of our senses, our hands, our minds, touching a reality that until this very moment we could only imagine. This is more than a technological achievement. It is a philosophical transition point, a moment of speciation for our curiosity. We are no longer confined to the cradle. We have taken our first tentative step into the cosmic neighbourhood. The data Voyager is sending back now is utterly unique, a letter from a new world. It is sampling for the very first time the pristine material from which future stars and planets will be born. It is measuring the magnetic fields that thread through our spiral arm of the galaxy, the invisible architecture that shapes the cosmos. It is charting the unknown, drawing the first crude maps of the interstellar currents. Each faint whisper received here on Earth is a pixel in a new portrait of our universe, one painted from a perspective we have never had before. It travels now at over 38,000 miles per hour, a speed that defies easy comprehension. Yet even at this velocity, space is so incomprehensibly vast that its journey has only just begun. It will not approach another star for 40,000 years. Its golden record may sail on for 1 billion years, a silent, glittering emissary, long after the Earth itself has been swallowed by our dying sun. It is in a very real sense our first attempt at immortality, a legacy project on a scale we can barely fathom. It is the ultimate expression of the human drive to see what lies over the next hill beyond the next ocean past the next star. It is the embodiment of our refusal to be bound by our horizons, and so we listen. We point our greatest radio telescopes toward a tiny patch of sky and strain to hear that faint fading signal. We listen for the health reports, the temperature readings, the particle counts. We listen for the story it has to tell about the great dark ocean it now sails. For this is no longer just Voyager's journey, it is our journey. It is our first chapter in a much larger story, the story of our species' entry into the galaxy. The new data streaming back is more than just numbers. It is a postcard from the frontier, a frontier that Voyager 1 has single-handedly pushed beyond the limits of our home and into the true beginning of everything else. How do you hear a whisper from across the solar system, not with an ear, but with an equation? In the mid-1960s, a graduate student at Caltech, Gary Flandreau, was given a seemingly tedious task by NASA's Jet Propulsion Laboratory. He was to calculate the most efficient trajectories to the outer planets, a bit of routine navigational homework. But as he plotted the orbits, as he ran the numbers through humming mainframe computers, a pattern began to emerge. It was a subtle alignment, a gravitational secret the solar system had been keeping for nearly 2 centuries. He discovered that in the late 1970s, Jupiter, Saturn, Uranus and Neptune would arrange themselves in a rare sweeping arc on one side of the Sun. This was no mere celestial coincidence. It was an invitation, an alignment so perfect, so serendipitous it wouldn't happen again for another 176 years. For the dreamers at JPL, this wasn't just data, it was a map to a hidden treasure. It meant a single spacecraft could, in theory, visit all 4 gas giants. It could use the immense gravity of each world as a celestial slingshot, a cosmic accelerator stealing a sliver of its orbital momentum to fling itself onward to the next target. The journey, which would normally take 40 years to reach Neptune alone, could be cut down to just 12. The concept was breathtaking in its audacity, a once-in-a-lifetime opportunity to peel back the veil on the most mysterious and distant members of our solar family. They called it quite simply the Grand Tour. It was the Apollo of the outer planets, a mission so ambitious it bordered on science fiction, promising to transform our planetary atlases from vague sketches into richly detailed portraits. The late 1970s were a peculiar time for such dreams. The roar of the Saturn V rockets that had carried humanity to the moon was fading into memory. The manic unifying energy of the space race had given way to economic anxieties and a more pragmatic, earth-bound focus. Yet in the sun-drenched, low-slung buildings of JPL in Pasadena, California, the dream of the Grand Tour burned with the intensity of a thruster burn. Here, a guild of slide rule sorcerers and engineering pioneers, veterans of the Mariner and Pioneer missions, began to sketch the impossible. They envisioned not one, but a fleet of advanced probes built to withstand the punishing radiation of Jupiter, the cryogenic cold of deep space, and the sheer unending loneliness of a multi-decade journey. These would be the most sophisticated, most autonomous robotic explorers ever conceived humanity's proxies sent on an odyssey to worlds we had only ever glimpsed as faint, flickering points of light in our largest telescopes. The vision was glorious, a symphony of orbital mechanics and technological ambition. The price tag, however, was staggering. As the estimated cost ballooned toward $1 billion, the dream collided with the harsh reality of politics and budgets. In Washington, the Grand Tour was seen as a spectacular but unaffordable luxury. The program was unceremoniously cancelled in 1972, its promise seemingly extinguished before it could even begin. For the teams at JPL, it was a devastating blow. The celestial window was closing, the planets slowly and inexorably moving out of their perfect alignment. The chance of a generation was slipping through their fingers. But the dream was too powerful to die completely. Out of the ashes of the Grand Tour, a leaner, more focused and perhaps even more ingenious mission was born. It would be a 2-spacecraft journey targeting only Jupiter and Saturn, the 2 colossal gas giants that held the keys to understanding the outer solar system. It was a compromise, a shadow of the original vision, but with one crucial, brilliant caveat. The engineers, in a stroke of defiant optimism, would design these twin spacecraft with the soul of the Grand Tour intact. They would build them to last. They would calculate the trajectory for Jupiter and Saturn, yes, but they would aim Voyager 2 with such exquisite precision that if it survived its first 2 encounters, the option to continue on to Uranus and Neptune would remain open. A long shot, a hope whispered into the vacuum of space. The mission was christened Voyager, a simple, elegant name for what would become the most extraordinary journey of exploration in human history. To us, they are now legends, icons of discovery. But back then, you have to understand what they truly were. They were marvels of miniaturization and resilience crafted from aluminum gold and human ingenuity, each one weighing less than a small car. Imagine you're there in the clean rooms of JPL in 1977. The air hums with conditioned coolness and a palpable sense of anticipation. Before you stand the twin emissaries, Voyager, Swan and Voyager 2. They don't look sleek or aerodynamic, for in the frictionless void where they are destined to fly, such concepts are meaningless. They are intricate, almost fragile-looking assemblies of instruments. Booms and dishes, a testament to function over form. A massive 10-foot-wide, high-gain antenna dominates each craft, a parabolic ear cocked and ready to listen for the faint commands from Earth and to whisper back its discoveries across hundreds of millions of miles. This antenna is their voice and their lifeline. Extending from the main body on a long truss is the science boom, a celestial Swiss Army knife, carrying a suite of instruments designed to taste, see and feel the environments they would fly through. Magnetometers to map the invisible magnetic fields that enshroud these giant worlds. Plasma detectors to sample the solar wind, that constant stream of charged particles blowing out from our sun. Cosmic ray sensors to count the high-energy bullets ricocheting through the galaxy. And then there were their eyes. A pair of television cameras mounted on a steerable scan platform, a robotic neck that could swivel with uncanny precision. One camera for wide-angle contextual shots, the other a narrow-angle lens for breathtaking close-ups. These weren't digital cameras as we know them today. They used Vidicon tubes and older analog technology, painstakingly capturing images line by line, which would then be digitized and beamed back to Earth. The entire process was a marvel of patience, a slow-motion revelation. Yet the most profound challenge was not in seeing, but in thinking. The light time delay, the sheer time it took for a radio signal to travel from Earth to Jupiter and back, would be over an hour and a half. By the time a problem was detected on Earth, it would be far too late to send a command to fix it. The probes had to be smart. They had to be autonomous. Their brains were a set of 3 interconnected computer systems, each with redundant backups. By modern standards, their memory was laughably small, about 69 kilobytes, less than a single low-resolution photo on your phone. But the software written by the engineers at JPL was a masterpiece of efficiency. It allowed the Voyagers to execute complex pre-programmed sequences of commands to diagnose their own problems and to switch to backup systems if something went wrong. They were programmed not just with instructions, but with an instinct for survival. Powering this intricate machine was another piece of revolutionary engineering. Solar panels were useless in the dim twilight of the outer solar system, so the Voyagers carried their own miniature power plants, radioisotope thermoelectric generators or RTGs. These devices mounted on a boom far from the sensitive science instruments contained plutonium-238. As the plutonium naturally decayed, it released a steady, reliable flow of heat, which was then converted directly into electricity. It was a fading atomic heartbeat designed to keep the probes alive for decades long after they had sailed past the last rays of sunlight strong enough to power a spacecraft. But perhaps the most poignant and audacious component bolted to the side of each Voyager probe was not a scientific instrument at all. It was a message, a greeting card to the cosmos. Conceived by a committee led by the brilliant astronomer Carl Sagan, the Golden Record was a 12-inch gold-plated copper disc, a time capsule carrying the sights and sounds of our world. It contained 115 images encoded in analog form, showcasing life on Earth, our science, our art, and our humanity. It carried greetings in 55 different languages from ancient Akkadian to modern Mandarin, each one a small, hopeful voice cast into the cosmic ocean. And it contained music, a 90-minute selection that ranged from Bach and Beethoven to Chuck Berry's Johnny B. Good and the haunting chants of Melanesian tribesmen. It was a love letter to any civilization that might one day find it a statement that in this small blue corner of the universe, a species arose that could dream, that could create, and that dared to reach for the stars. On its protective cover were etched simple diagrams, a map of our solar system, instructions on how to play the record and the location of our sun, relative to 14 nearby pulsars, a celestial address written in the language of physics. It was an act of profound, almost irrational optimism, a belief that we were not just explorers but communicators ready to join a galactic conversation, even if the response might take millennia. The entire endeavour hinged on a manoeuvre that had been tested, but never on this scale, the gravity assist. It's a concept of pure elegance, a gravitational dance of breathtaking consequence. You don't just fly past a planet, you engage with it. As the spacecraft approaches a colossal world like Jupiter, it falls into the planet's immense gravitational well, accelerating dramatically. It is like a skater dropping into a deep bowl. The probe then swings around the planet's far side, climbing back out of the gravity well, but it does so in the direction of the planet's own orbital motion. In this cosmic transaction, the spacecraft steals a tiny, imperceptible fraction of the planet's immense orbital energy. The planet is slowed in its path around the Sun by an amount so infinitesimal it is completely immeasurable, but the small light spacecraft is violently accelerated, its trajectory bent, its speed boosted by thousands of miles per hour. It's a gravitational heist, a perfectly executed cosmic slingshot that gives you a massive kick of velocity for free-saving years of travel time and tons of fuel that you would never have been able to carry. The Voyager mission was a chain of these maneuvers, a game of celestial billiards, where each shot had to be perfect, calculated to the kilometre to set up the next 1 millions of miles away. A tiny error at Jupiter would mean missing Saturn by a continent. An error at Saturn would mean missing Uranus by a planet's width. The mathematics had to be flawless. The launch window opened in the late summer of 1977. Despite its name, Voyager 2 was the first to leave. It was launched on August 20th, placed on a slower, longer trajectory that preserved the option for that far-flung journey to Uranus and Neptune. 16 days later, on September 5th, it was Voyager 1's turn. It was placed on a faster, more direct path to Jupiter. From the viewing stands at Cape Canaveral, you could feel the ground tremble. The massive Titan III rocket, a pillar of white fire and thunder, ignited its engines, straining against the pull of Earth's gravity. For the engineers who had poured years of their lives into these machines, this was the moment of truth. Years of calculations, of sleepless nights, of meticulous assembly, all culminating in this controlled, terrifying explosion. As the rocket clawed its way into the Florida sky, it carried more than just a payload of scientific instruments. It carried the distilled curiosity of an entire species. It was our ambition made manifest, a 360-foot spear of fire hurled at the heavens. The ascent was flawless. The stages separated, each one falling away as its fuel was spent, until only the Voyager spacecraft and its final kick stage remained coasting in the silent blackness of Earth orbit. Then, with one final precise burn, the spacecraft was flung out of Earth's embrace, its velocity climbing to over 36,000 miles per hour. It was on its way. From the probe's perspective, Earth would have rapidly shrunk from a vibrant, swirling marble of blue and white into a brilliant star-like point of light indistinguishable from the countless others that filled the void. The umbilical cord was cut. For the first time, the Voyagers were on their own, flying silent and true through the interplanetary darkness. They began to unfurl, deploying their long booms for the magnetometers, and the RTGs slowly coming to life. They checked their systems, oriented themselves by the sun and the star Canopus, and settled in for the long cruise. Ahead of them lay the asteroid belt, a cosmic minefield they had to navigate, and beyond that their first colossal target, a world of storms and moons, a miniature solar system in its own right, the king of the planets, Jupiter. The first chapter of the Great Journey had just begun, a journey that would lead us through the wonders of our solar system and then impossibly beyond. And so, after surviving the gauntlet of the asteroid belt, our tiny emissary sailed onward through the deepening twilight. For years it was a silent vigil in the void, a patient journey across a gulf of space so profound it strains the human imagination. The sun, our brilliant life-giving star, shrank behind it, its warmth becoming a distant memory, its light a fading beacon. Ahead lay a new frontier, a realm not of rocky worlds and thin atmospheres, but of giants of titans sculpted from the primordial gas and dust that our own small planet had left behind. The first of these titans began as a pinpoint of light indistinguishable from the stellar backdrop, but week by week it grew swelling in Voyager's electronic eye until it consumed the forward view, no longer a point of light but a world. This was Jupiter, the king of planets, a failed star whose immense gravity had shaped the architecture of our entire solar system. You have seen the photographs, the iconic images of a banded, swirling giant, a marble of ochre cream and burnt sienna. But to witness it as Voyager did is to understand that these are not mere pictures of a planet. They are portraits of a storm so vast it has raged for centuries, a tempest that could swallow our Earth 3 times over. Voyager's flyby was not a gentle cruise, it was a violent plunge, a high-speed dive through a treacherous realm of lethal radiation. Jupiter's magnetic field, a colossal invisible cage spun by the planet's metallic hydrogen core. Trapped charged particles, whipping them into radiation belts 1,000 times more intense than Earth's Van Allen belts. This was a particle accelerator of planetary proportions, a sea of deadly energy that threatened to fry Voyager's sensitive electronics, to erase its memory, to blind it, just as it arrived at its destination. Engineers on Earth had shielded its circuits as best they could, but they could only hold their breath as our probe braved the onslaught. For 18 agonizing months it fell toward this maelstrom, and with every passing moment the data that streamed back across 500 million miles of space began to paint a picture more complex, more violent and more beautiful than anyone had ever dared to dream. The great red spot, that famous crimson eye, was revealed not as a static feature, but as a titanic anticyclone, a hurricane of unimaginable scale, with winds screaming at 400 miles per hour. Voyager's cameras capturing time-lapse sequences showed us a fluid dynamic world, a boiling cauldron of atmospheric chemistry, where rising plumes of ammonia ice crystals formed the bright zones, and descending gases tinged with unknown chemical compounds created the darker, warmer belts. For the first time, we saw lightning flashes in another planet's clouds, bolts of electricity powerful enough to dwarf any terrestrial storm, and we detected colossal auroras at its poles, ghostly curtains of light dancing in response to the ceaseless bombardment of particles. Jupiter was not a placid ball of gas, it was a living, breathing entity, a meteorological beast of terrifying power. Yet the true revolution, the discovery that would fundamentally alter our search for life in the cosmos, was not the planet itself, it was its moons. Until this moment, we viewed moons as our own, as barren, silent, cratered companions, geologically dead for eons. But the 4 great Galilean moons, first spotted by Galileo in 1610, were about to shatter that paradigm forever. The first to come into focus was Io, and what Voyager saw sent shockwaves through the scientific community. This was not a dead world. It was a world of fire. The images revealed a surface unlike anything ever seen, a landscape painted in nightmare shades of yellow, red and black, pockmarked not by craters, but by the dark calderas of active volcanoes. A young navigation engineer, Linda Morabito, examining an image to pinpoint Voyager's exact location, noticed a strange umbrella-shaped plume erupting from the moon's limb silhouetted against the blackness of space. It was an active volcanic eruption spewing sulfur and ash hundreds of miles into the sky. Io was and is the most volcanically active body in the solar system. It is a world caught in a gravitational tug-of-war, stretched and squeezed by the immense pull of Jupiter on one side and the rhythmic tugs of its sibling moons on the other. This constant tidal flexing generates incredible heat in its interior, turning it into a molten hellscape, a geological furnace that continuously repaves its own surface. Then came Europa. At first glance, it seemed Io's complete opposite. Where Io was a canvas of violent colour, Europa was a serene, brilliant white sphere, a billiard ball of ice. But as Voyager drew closer, its cameras revealed a surface that was not smooth, but fractured, covered in a complex web of cracks and dark reddish streaks, as if a fine porcelain shell had been shattered and then frozen back together. Most startlingly, there were almost no impact craters. This meant the surface was young, constantly being renewed from below. Something was erasing the scars of cosmic history. For the first time, humanity was confronted with the tantalizing evidence of a vast liquid water ocean hidden beneath that global shell of ice. The implications were staggering. Here in the cold outer darkness so far from the sun's warmth was a potential habitat for life kept liquid by the very same tidal forces that tortured Io into a world of fire. It was a message in a bottle written in scars of ice, a promise that the ingredients for life might exist in the most unexpected of places. Ganymede, larger than the planet Mercury, revealed a complex history of tectonic upheaval, its ancient cratered terrain crisscrossed by younger, brighter grooves and ridges. And Callisto, the outermost of the 4, appeared as a battered relic, its surface ancient and saturated with craters, a silent testament to the violent youth of our solar system. In a single breathtaking flyby, our entire conception of moons had been rewritten. They were not just satellites. They were worlds each with its own unique story, its own distinct personality and its own profound mysteries. Propelled by Jupiter's immense gravity, Voyager was flung onward, its velocity massively increased by the gravitational slingshot. Its new target lay 2 years and nearly another billion miles away, Saturn, the ringed jewel of the solar system. If Jupiter was a king of brute force and raw power, Saturn was an artist of sublime ethereal beauty. As Voyager closed the distance, the rings which from Earth appear as a solid, graceful band resolved into a structure of breathtaking complexity. They were not solid at all, but a shimmering celestial river composed of countless individual particles of water ice, ranging in size from specks of dust to chunks as large as mountains. Voyager discovered that this river was divided into thousands of distinct razor-thin ringlets, an intricate system of grooves and gaps that resembled nothing so much as a cosmic phonograph record. And just like a record, these grooves held a story, a history of gravitational resonances with Saturn's many moons. We discovered tiny shepherd moons whose gravity acts like a containing force, sculpting the sharp edges of the rings. We saw strange dark radial features called spokes that formed and dissipated within hours, ephemeral structures created by electrostatic forces lifting fine dust above the main ring plane. And we witnessed the bizarre braided structure of the F-ring, a chaotic intertwined ribbon of ice particles that seemed to defy the elegant laws of orbital mechanics. It was a vision of impossible celestial architecture, a display of physics so intricate and delicate it felt almost alive. The moons of Saturn offered their own portfolio of wonders. There was Mimas with its one enormous crater that gave it the uncanny appearance of a science fiction battle station. There was Enceladus, a small moon so brilliantly white it reflected nearly 100% of the sunlight that struck it, a clue to a pristine icy surface that hinted at a geologically active interior, a secret that would only be fully revealed decades later. But the main event, the target that would dictate the rest of Voyager 1's existence, was the enigmatic moon Titan. Larger than Mercury, Titan was unique, the only moon in the solar system shrouded in a thick opaque atmosphere. Voyager's cameras could not pierce its dense orange haze, but its instruments could taste that atmosphere, could analyse its composition. They found it to be overwhelmingly nitrogen, just like Earth's. But here the nitrogen was mixed with methane and other hydrocarbons, creating a primordial chemical soup under a deep freeze. It was like a vision of a prebiotic Earth cryogenically preserved, a laboratory for studying the very chemical pathways that may have led to life on our own world. And here in the shadow of Saturn, the mission reached its critical turning point. The primary objectives were complete. The grand tour of Jupiter and Saturn had been a success beyond the wildest dreams of its creators. Now a choice had to be made, a decision that would seal Voyager's fate. There were two paths forward. One path would take the spacecraft on a trajectory to visit Uranus and Neptune, completing the full grand tour as its twin Voyager 2 would later do. But this path meant sacrificing a close flyby of Titan. The other path, the one that offered the best possible scientific data on Titan's mysterious atmosphere, required a very specific trajectory, a dive that would use Saturn's gravity to bend its course dramatically. This maneuver, this final gravitational kiss goodbye, would act as a powerful accelerator, but it would also hurl Voyager 1 upwards out of the ecliptic plane, the flat disk where all the planets orbit, and send it on a trajectory that would never encounter another world. It would be a one-way journey into the unknown, a final departure from the planetary family. The choice was made. For the chance to get one last definitive look at the atmosphere of Titan, the team at the Jet Propulsion Laboratory chose the path of no return. They chose interstellar space. With that final perfectly executed maneuver, Voyager 1's planetary mission was over. Its gaze swung back for one last look, and from a distance of nearly 4 billion miles at the request of Carl Sagan, it began to take a final series of photographs. This was the family portrait, a mosaic of our home system, as seen from the outside, and in that collection of images captured by a machine that was now destined to wander the void forever, was one particular frame. A single pale blue pixel suspended in a scattered beam of sunlight. That was us. That was Earth. A tiny, fragile mote of dust, our whole world, everyone you have ever known, contained in a single speck of light against the immense cosmic dark. It was a perspective-altering moment of profound humility, a final poignant wave goodbye from our most distant explorer. With its cameras powered down to conserve energy for the long journey ahead, Voyager 1 sailed into a new and emptier ocean. The years stretched into decades. The sun, our magnificent star, dwindled to become just the brightest point of light in a sky crowded with unfamiliar constellations. The cold deepened, an absolute bone-deep cold that permeates the outer darkness. The mission changed. It was no longer a mission of exploration in the visual sense of capturing breathtaking images of new worlds. It became a mission of perception, of feeling its way through an invisible and unknown environment. Its instruments were now sampling the very medium of space itself, listening to the faint whispers of the cosmos. The primary quarry was the solar wind, the constant stream of charged particles flowing outwards from the sun. This wind inflates a gigantic magnetic bubble around our solar system, a protective cocoon called the heliosphere. For its entire life, Voyager had been swimming within this bubble, shielded by it from the harsh radiation of interstellar space. But now it was approaching the bubble's edge. Scientists on Earth, many of whom had not even been born when Voyager was launched, watched their monitors with a patient generational vigilance. They were waiting for a sign. And slowly, subtly, the signs began to appear. The data trickling back across, now billions upon billions of miles, began to register a change in the environment. The speed of the solar wind, which had been racing outwards at over 1 million miles per hour, began to slow down as if it were running into an unseen obstacle, a cosmic headwind. Simultaneously, another instrument began to register something new. Its cosmic ray subsystem, designed to detect high-energy particles originating from distant supernovae and other violent cosmic events, started to record a gradual increase in impacts. For decades, the heliosphere had acted as a shield, deflecting the majority of these galactic cosmic rays. But as Voyager pushed further out, that shield was beginning to thin. It was like walking away from a roaring campfire on a cold night. You begin to feel the chill of the surrounding wilderness, and you can hear the distant sounds of the forest more clearly. Voyager was feeling the chill of interstellar space, and it was beginning to hear the symphony of the galaxy. The changes were not dramatic. They were gradual, painstakingly slow, playing out over years. The solar wind velocity would drop slightly, then hold steady. The galactic cosmic ray count would tick upwards, then plateau. It was a delicate dance of competing forces, the fading breath of our sun pushing outwards, against the immense steady pressure of the interstellar medium pushing inwards. Voyager was entering a turbulent transitional zone, a cosmic shoreline where the solar sea crashes against the interstellar ocean. The data grew stranger, more difficult to interpret. The magnetic field lines, which should have been flowing smoothly out from the sun, began to pile up, becoming stronger and more compressed. The smooth flow of particles became a chaotic jumble. The probe was no longer in the comfortable, predictable realm of the sun's undisputed dominion. It was approaching a boundary, an invisible wall of plasma and magnetic force that no human-made object had ever touched. It was approaching the termination shock, the place where the solar wind collides with the interstellar medium and slows abruptly from supersonic to subsonic speed. This was the first great frontier of interstellar space, the true beginning of the end of our sun's influence. And as Voyager 1 raced towards it at more than 38,000 miles per hour, the team on Earth could only watch their data streams, holding their collective breath, waiting for the moment of impact, the moment our tiny, aging messenger would finally cross over and tell us what it feels like to confront the true void. And so for years, the transmissions from Voyager 1 told a story of a place that shouldn't exist. It was a cosmic waiting room, a bizarre and unanticipated purgatory, poised on the very threshold of interstellar space, yet stubbornly refusing to cross it. The delta coming back to Earth, trickling across billions of miles of emptiness, was not the clean, crisp narrative of a journey's end that science had predicted. Instead, it was a fragmented, deeply perplexing puzzle, a set of clues that seemed to contradict one another at every turn. The team at the Jet Propulsion Laboratory, custodians of this lonely traveller, found themselves in the grip of a profound scientific mystery. They had spent their careers preparing for a singular moment, for the telltale signs that would announce humanity's arrival in the galactic expanse. They expected a clear signal, a definitive line drawn in the void. What they received was a whisper, a riddle, a paradox wrapped in the language of magnetic fields and charged particles. The first profound clue, the one that truly quickened the pulse of the mission scientists, arrived in the late summer of 2012. It came from an instrument designed to listen to the cacophony of the cosmos, a detector for cosmic rays. For decades, it had diligently measured two distinct populations of these energetic particles. The first were the anomalous cosmic rays born within our solar system, trapped and accelerated by the sun's vast magnetic bubble, the heliosphere. These were the familiar natives, the particles of home. The second group were the galactic cosmic rays, true interstellar travellers forged in the hearts of distant supernovae and flung across the galaxy for eons. For most of Voyager's journey, These galactic invaders had been held at bay, deflected by the protective shield of the heliosphere. You can imagine it as standing inside a fortress, hearing only the muted sounds from your own courtyard, while a raging storm, the symphony of the galaxy, howls just outside the walls. Then on the 25th of August, the walls simply vanished. Over a period of mere hours, the data stream shifted with an astonishing, almost violent finality. The familiar hum of anomalous cosmic rays, the particles born of our sun, plummeted by a factor of 1,000. They didn't just dwindle, they effectively disappeared as if a switch had been thrown across the solar system. Simultaneously, the intensity of galactic cosmic rays, the messengers from deep space, spiked to levels never before seen, a flood of alien energy pouring in from all directions. It was the clearest, most dramatic signal yet. The fortress had been breached. The shield was down. This had to be it. The long-awaited crossing. A wave of quiet, cautious elation swept through the science teams. They had seen the most unambiguous sign that Voyager was no longer bathing in the sun's environment. It was now being scoured by the raw, unfiltered energy of the galaxy itself. This abrupt change was a textbook indicator of an exit, a moment etched into every model of the heliosphere's edge. They had passed through the gate. They had to have. But science demands more than a single piece of evidence, no matter how compelling. The universe is notoriously clever at crafting illusions, at presenting phenomena that mimic our expectations. Corroboration was essential, and the second critical piece of the puzzle lay with the magnetic field. And it was here that the beautiful, simple story of a clean exit began to unravel. Every theory, every computer simulation predicted a fundamental shift in the magnetic field's orientation. Think of the sun's magnetic field as a vast spiraling structure shaped by the sun's rotation. Its lines of force are largely aligned with the sun's equator, an invisible grain flowing outwards through the solar system. The interstellar magnetic field, however, is a different beast entirely. It's the faint, ancient field of the Milky Way itself, shaped by the combined magnetism of billions of stars and nebulae. It has its own direction, its own orientation, completely independent of our sun. Crossing the boundary between these two domains, the heliopause should have been like crossing a cosmic weather front. The direction of the magnetic compass aboard Voyager 1 was expected to pivot to swing around and align itself with this new galactic magnetic direction. It was the mission's most anticipated signal, the definitive proof of passage. The scientists waited. The days turned into weeks, the weeks into months. The galactic cosmic rays continued to flood the sensors, screaming that Voyager was outside. Yet the magnetometer data remained stubbornly, maddeningly unchanged. The magnetic field refused to turn. It was as if you had walked out of your house, felt the wind and the rain of a hurricane on your face, but looked at your compass and found it still pointing resolutely toward your living room. It made no sense. This was the great paradox that plunged the team into months of intense, sometimes fractious debate. How could Voyager be in two places at once? How could one instrument declare it was flying through interstellar space, while another insisted it was still firmly tethered to the sun's magnetic influence? This wasn't just an academic puzzle. It challenged our fundamental understanding of how our solar system interacts with the galaxy. Was the heliopause not a simple boundary, but a far more complex, layered and porous region than anyone had imagined? Had Voyager entered a bizarre transitional zone, a magnetic twilight, where the rules of both realms were bent and broken, the science team split into factions? One camp argued that the cosmic ray data was undeniable. Such a sharp, sustained change could only mean one thing: Voyager was out. The magnetic field, they theorized, must be behaving in some unexpected way. Perhaps the interstellar field just happened to be aligned with the solar field at that specific point in space and time, an incredible coincidence, but not an impossibility. Or maybe the interstellar field was draping itself over the heliosphere like a cloth over a ball, creating a region where the direction remained temporarily constant. The other camp held firm to the magnetic field theory. For them, a change in direction was the gold standard, the non-negotiable proof. Without it, the cosmic ray data, however dramatic, had to be some other exotic phenomenon occurring within the boundary itself. They argued that proclaiming Voyager's exit prematurely would be a historic error, a rush to judgment. The burden of proof, they insisted, was absolute. For nearly a year, the stalemate persisted. Voyager continued its silent journey, broadcasting its confounding secrets back to a divided community of scientists. The probe itself, indifferent to the human drama it was causing, was now more than 18 billion kilometers from home, a distance so vast it felt more like an abstraction than a reality. Each packet of data took more than 16 hours to reach Earth, a faint whisper carrying the fate of one of humanity's grandest explorations. The team needed a tiebreaker, a third independent piece of evidence so clear it would settle the debate once and for all. They found it not by looking for it, but by a stroke of cosmic luck, a final spectacular gift from the very star Voyager was leaving behind. The key lay with an instrument that had been largely silent for years, the plasma wave subsystem. This device doesn't see particles, it listens to them. It's designed to detect the oscillations of plasma, the thin electrified gas that permeates space. By measuring the frequency of these vibrations, scientists can deduce the density of the plasma itself. It's like tapping a bell. The pitch of the ringing tells you what the bell is made of and how dense it is. Inside the hot, tenuous bubble of the heliosphere, the plasma is incredibly sparse. Voyager's plasma wave instrument had heard very little for a very long time. Interstellar space, by contrast, was predicted to be far denser. Not dense by earthly standards, of course, it's a far better vacuum than any we can create in a lab. But relative to the Sun's domain, it was expected to be a thick, soupy medium, perhaps 40 to 100 times denser. If Voyager were truly outside, a measurement of this high-density plasma would be the smoking gun. The problem was the plasma out there was cold and quiet. It wasn't vibrating on its own, so the instrument had nothing to hear. Voyager needed something to come along and strike that interstellar bell. In March of 2012, long before the cosmic ray debate had even reached its peak, the Sun obliged. It unleashed a colossal coronal mass ejection, a massive eruption of solar material, and flung it out into the solar system in all directions. This solar tsunami, travelling at millions of kilometers per hour, began its own epic journey outwards. For 13 long months it raced through the solar system well past the orbits of all the planets, a shockwave of the Sun's power expanding into the void. The science team on Earth tracked its progress, but its ultimate significance was not yet apparent. Then, in April of 2013, that 13-month-old solar storm finally reached Voyager 1's location. The wave of energy, the last echo of the Sun's fury, slammed into the space surrounding the probe, and suddenly, the plasma that had been cold and quiet began to sing. The plasma wave subsystem, dormant for so long, awoke. It registered a clear rising tone, the distinct signature of oscillating plasma. The interstellar medium was ringing like a bell struck by a hammer forged in the heart of our own solar system. Don Gurnett, the principal investigator for the instrument, and his team analysed the frequency of that tone. They worked backwards, calculating the density of the plasma that must be producing it. The number they arrived at was stunning. The plasma around Voyager 1 had a density of 0.08 electrons per cubic centimetre. It was a tiny number, but it was nearly 80 times denser than the last measurements taken inside the heliosphere. It perfectly matched the predictions for the density of the interstellar medium. They had their proof. The sound was undeniable. When they looked back through older data, they found another fainter tone from a weaker solar event that had reached Voyager in the autumn of 2012. That event, they now realised, had occurred in late October. But the dramatic cosmic ray drop-off had happened back in August. This meant that when the first, most powerful clue arrived, Voyager was already outside. The crossing had happened on or around August 25, 2012. The debate was over. The magnetic field's stubborn refusal to change was still a profound mystery, a puzzle for a future generation, hinting that the boundary of our solar system is a far more complex and magnetically turbulent place than we knew. But the convergence of the other evidence was overwhelming. The galactic cosmic rays were the roar of the ocean. The plasma density was the taste of salt in the air. Voyager 1 was no longer sailing on the river of the Sun. It had reached the open sea of the galaxy. The announcement, when it finally came in September of 2013, was a moment that redrew the map of human exploration. It was delivered not with fanfare and celebration, but with the quiet, profound weight of history. For the first time, a human-made object had exited the warm protective cocoon of its birth star and entered the vast, ancient and unknown realm between the stars. Every previous journey in human history had been a journey to a place. This was a journey from a place. It was an act of severance of departure on the grandest scale imaginable. We had not just visited another world, we had left our own world, our entire system of worlds behind. The heliosphere, which for so long had defined the outer limit of our cosmic backyard, was now a feature in Voyager's rearview mirror. Its official boundary, the heliopause, was no longer a theoretical line in a textbook. It was a real place with a date and a time of crossing stamped upon it by our own intrepid emissary. This single definitive moment transformed our perception of our place in the cosmos. We were no longer just inhabitants of a solar system. We were now officially participants in the galactic neighbourhood. Our longest journey had reached its most profound destination. The door had been opened, the threshold crossed. But this was not an ending. It was a spectacular beginning. For beyond that threshold lay a universe utterly new, to direct experience, a frontier filled with the dust of dying stars and the seeds of new ones. Now for the first time we had a witness there, and the story it was about to tell would be even stranger, more wondrous and more challenging than anything we had encountered on the long road to leaving home. The first interstellar dispatch was about to arrive. The echo of that final triumphant crossing has now faded. The cosmic shoreline we watched Voyager 1 breach that turbulent frontier where the sun's breath finally gives way is now a memory receding in its wake. There are no more boundaries to cross, no more great walls of our own making to tear through. There is only the onward, the outward, the forever. And with this new reality comes a profound and chilling silence, a quiet that settles not just in the void between the stars but here in our hearts. For the grand ascent, the climactic escape is over. Now begins the long downward path, a journey defined not by what is gained but by what is slowly, inexorably being lost. It begins with the tyranny of time and distance, a gap so vast it beggars belief. 15 billion miles. The number is an abstraction, a string of zeros that fails to convey the crushing isolation it represents. Think of it this way. When you send a message to a friend across the planet, light travelling through fibre optic cables delivers it in a fraction of a second. When Mission Control sends a command to Voyager 1, that message travelling at the absolute fastest speed the universe allows takes more than 22 hours to arrive. One full rotation of our Earth. A day and a night must pass before our words even reach the lonely craft. And then we must wait again. Another 22 hours for Voyager to process the command, gather its precious data, and whisper its reply back across the void. A single question and answer, the most fundamental form of communication, now requires nearly 2 full days to complete. It is a conversation held across an impossible gulf, a dialogue where each participant must wait for the other's ghost to speak. The team on the ground has learned a new form of patience, a geological sense of time. They live their lives in this 44-hour echo, sending their hopes out into the darkness, and then waiting through meetings and meals, through sunsets and sunrises, for the faint reply from their steadfast emissary. This delay warps everything. There can be no real-time adjustments, no quick fixes for a sudden unexpected problem. Every command must be crafted with meticulous foresight, anticipating what the probe's environment will be 2 days from now, praying their predictions are correct. They are steering a ship whose helm they can only touch once every 2 days, navigating a cosmic ocean whose currents are utterly unknown. This temporal chasm is a constant humming reminder of just how far away we are and how fragile this connection has become. The thread of contact, once a robust lifeline, is now stretched so taut it has become almost invisible, vibrating with a message from a world that is for Voyager already in the past. Compounding this crushing distance is a far more finite problem, the slow, inevitable dimming of the light. Voyager 1 is not powered by the sun. Out here, our star is just the brightest point of light in a crowded field, its life-giving energy reduced to a pathetic glimmer, utterly insufficient to power even the smallest instrument. Instead, the probe's lifeblood flows from a heart of fading fire, a device born of Cold War ingenuity called a radioisotope thermoelectric generator. Deep within its core, 3 capsules of plutonium-238, forged in the heart of nuclear reactors, have been decaying for nearly half a century. As each atom of this exotic element breaks down, it releases a tiny puff of heat. This warmth, captured by an array of thermocouples, is converted directly into a trickle of electricity. It is a nuclear battery and atomic furnace with no moving parts, designed to endure for decades in the most hostile environment imaginable. When it left Earth, this atomic heart beat strongly, providing over 470 watts of power, enough to run all of its instruments, its transmitters, its heaters, and its primitive but brilliant computer brain. But the fire inside is not eternal. Plutonium-238 has a half-life of 87.7 years. Every second of every day since launch, a little less of it exists. A little less heat is generated, a little less power flows through Voyager's veins. The decay is agonizingly, beautifully, tragically predictable. Today, that 470-watt torrent has dwindled to a stream of less than 250 watts. The probe is now operating on less power than it takes to illuminate a few household light bulbs, and so the science of this mission has become a science of sacrifice. Voyager's human caretakers, some of whom have spent their entire careers listening to this machine, are now forced to make heartbreaking choices. They have become the stewards of a slow decline, managing a celestial power budget, where every milliwatt is precious. Years ago, they began the process shutting down non-essential systems one by one. First went the heaters for instruments that had completed their primary planetary missions. The imaging cameras, the eyes that showed us the Great Red Spot and the rings of Saturn in breathtaking detail, were switched off forever in 1990, their purpose served. Then more recently, the cuts became more painful. Heaters for the magnetometer boom, crucial for keeping the sensitive instrument stable. Heaters for the cosmic ray subsystem. Each shutdown is a calculated risk, a gamble that the unheated electronics now exposed to the near absolute zero cold of interstellar space will somehow continue to function. It is a chilling triage performed across billions of miles. The engineers send their commands, plunging another part of the distant craft into profound cold, and then hold their breath for 2 days, waiting to see if it survived the shock. This is the new reality, a constant gnawing anxiety, a battle against an enemy that cannot be defeated, the simple, relentless passage of time. The team is no longer asking what new wonders can we discover. They are asking a much more desperate question. What can we live without just to keep the heart beating for one more day? Each year the power budget shrinks by another 4 watts, a slow steady tightening of the noose. Eventually the power will fall below the threshold needed to operate even a single scientific instrument. Then it will fall below the level needed to run the transmitter, and on that day, the conversation will end. The whisper will finally irrevocably be consumed by the silence, and what a whisper it is. The signal we strain so desperately to hear is of an almost unimaginable faintness. Voyager's main transmitter broadcasts with a power of just 22 watts, less than the bulb in your refrigerator. This minuscule amount of energy radiates outwards from the probe's high-gain antenna in a wave, but it spreads. It expands over the 15 billion miles back to Earth, thinning out, becoming ever more diffuse. By the time this wave washes over our planet, the amount of energy falling on the entire surface of the Earth is infinitesimal. To capture it, we rely on the Deep Space Network, a global triad of colossal radio antennas in California, Spain, and Australia. These are the most sensitive ears humanity has ever built. Giant 70-meter dishes that pivot on enormous gears, tracking Voyager's predicted position in the sky with a precision that is nothing short of miraculous. They are engineered to hear a sound that is billions of times weaker than the static generated by their own internal electronics. The task can be compared to standing in the middle of a roaring hurricane and trying to hear the sound of a single snowflake landing on the ground miles away. The signal from Voyager 1, when it finally arrives, is a phantom. A ghost of a signal 20 billion times weaker than the battery in a digital watch. Sophisticated supercomputers must sift through an ocean of cosmic noise, the chatter of distant quasars, the hiss of our own galaxy, the background radiation of the Big Bang itself, all to isolate that one impossibly faint voice. They search for a unique frequency, a carrier wave that is Voyager's signature, its fingerprint in the ether. When they lock on, they can begin the painstaking process of decoding the data. It carries a stream of binary code flowing at a paltry 160 bits per second. At this rate, it would take you almost 3 hours just to download a single low-resolution photograph. But this data is more precious than any image. It is the only direct sensory information we have from the space between the stars. Each bit is a treasure fought for, captured and cherished. Every packet of information that survives the journey is a testament not just to the endurance of a machine, but to the sheer stubborn refusal of its creators to let go. It is an act of listening that borders on an act of faith, a belief that out there in the unending night our creation is still speaking to us, and that we against all odds can still hear what it has to say. What it speaks of is a place stranger than we ever imagined. The interstellar medium is not the placid empty void of popular fiction. It is a turbulent, energetic environment, a thin, cold soup of plasma and dust forged in the death of ancient stars and churned by galactic magnetic fields. Voyager 1, our first direct probe into this realm, has become our hands, our ears, our sense of touch in this alien territory. Its remaining instruments, though old, are painting a picture of a place fundamentally different from the protective bubble of our heliosphere. The plasma wave instrument, for instance, is detecting a constant low-frequency hum. When translated into the audible spectrum, it sounds like a low persistent moan, the background music of the galaxy itself. This is the vibration of interstellar gas, the plasma density far higher than inside our solar system's bubble. Voyager is telling us that the void is not silent. It has a voice, a song we are only now beginning to learn. Then there are the cosmic rays. Inside the heliosphere, the sun's magnetic field acts as a shield, deflecting the majority of these high-energy particles that zip through the galaxy at nearly the speed of light. But Voyager is now outside that shield. It is naked in the storm. Its cosmic ray subsystem shows that the intensity of these galactic bullets has skyrocketed. The probe is being constantly sandblasted by the radiation of 1,000 distant supernovas, a lethal environment that would fry any unprotected astronaut in an instant. This constant bombardment is a threat, a source of potential damage to its aging electronics, but it is also a vital clue. By measuring the energy and origin of these rays, we are learning about the most violent processes in our galaxy, using our tiny probe as a remote detector for stellar cataclysms that occurred thousands of years ago. Perhaps most baffling is the magnetic field. Scientists expected that as Voyager left the influence of our Sun, the local magnetic field would dramatically change direction, aligning with the broader galactic field. It did not. The magnetic field has grown stronger, more compressed, but its orientation remains stubbornly similar to the one forged by our own Sun. It's as if Voyager has crossed into a bizarre stagnant region of space just outside our home, a magnetic twilight zone that defies our models. Is the heliosphere draping its magnetic influence further out than we thought? Is there some unknown structure in the interstellar medium holding it in place? The data is sparse, the answers elusive. Every packet of information raises more questions than it answers, revealing a universe that is always more complex, more surprising, and more mysterious than we ever give it credit for. Voyager is no longer a planet hopper. It is a true explorer, charting the unknown, one faint burst of data at a time. This journey into the unknown is taking a toll not just on the power supply, but on the very mind of the machine itself. For 40 years, Voyager's attitude and articulation control subsystem, the RCS, performed its duties flawlessly. This is the part of the spacecraft's brain responsible for knowing where it is in space, and most importantly for keeping its main antenna pointed directly at Earth. Without it, all contact is lost. It is the gravitational gyroscope, the cosmic anchor, that makes communication possible. Then, without warning, the axe began to send back gibberish. Telemetry data that was garbled, nonsensical, reporting an orientation for the craft that was physically impossible even as the antenna remained miraculously locked onto Earth. It was as if the probe had lost its mind, yet its body continued to perform its most vital function perfectly. On Earth, panic set in. Was this the beginning of the end? Was the constant rain of high-energy cosmic rays finally corrupting its 1970s-era electronics? Engineers pored over schematics older than they were trying to diagnose a patient 15 billion miles away. They sent commands, waited 2 days for a response, and received only more corrupted data. The ghost in the machine was stirring, and for months no one knew why. They found a solution born of desperation and genius. The team hypothesized that the X was, for some unknown reason, trying to send its status report through a piece of onboard computer hardware that had failed decades ago. The old commands were being routed to a dead end. The solution: find a new path. They crafted a command to force the X to reroute its data through a different working part of the flight computer. It was a long shot, a piece of deep space neurosurgery performed with a 2-day delay. They sent the command. They waited. And then it came. A stream of clean, coherent telemetry. Voyager's mind for now was clear again. This incident was more than just a technical problem. It was a profound reminder of Voyager's reality. It is an old machine, a relic pushing through an environment it was never truly designed for. It is aging. Parts are failing. Like an old sailor, its joints ache, its memory falters, but its eyes remain fixed on the distant light of home. Each glitch is a new scar, each solution a testament to the bond between the machine and its makers. They are in this together, a partnership of human and automaton facing the final great darkness side by side. And as we follow this story, we are forced to confront the ultimate truth of this mission. This downward path does not end in a safe harbour. It ends in darkness. It ends in silence. One day, perhaps in the next few years, another critical heater will be turned off. Another instrument will fall silent. The trickle of power will become too faint to run the transmitter. The last whisper will be sent, the last bit of data captured, and the deep space network will listen, as it always does, only to hear the steady, indifferent hiss of the cosmos. The conversation after more than 50 years will be over, but Voyager's journey will not be. And then, after months of silence, after the long and agonizing work of sending whispers of code, across a gulf of 24 billion kilometers, the response came. Not as a sudden flood, but as a single perfect drop of water in a desert of static. A coherent packet of telemetry stripped of its former gibberish laid bare on the screens at the Jet Propulsion Laboratory. A collective breath held for what felt like an eternity was finally released. The ghost in the machine was gone. Voyager 1 was speaking to us again, and what it had to say would forever change our perception of the cosmic shores we have only just reached. This was not a message of greeting, nor was it a picture of some distant nebula. It was a stream of pure environmental data, a translation of the void itself. It was the answer to a question we barely knew how to ask. What does it feel like out there beyond the breath of our own sun? For its entire life, the probe had been swimming in a river of our own, making a relentless current of charged particles called the solar wind flowing outward from the sun in all directions. This was its home, its known universe. But where it is now is an entirely different realm, a place of profound otherness. It has plunged into the great galactic ocean, the true interstellar medium, and with its sensors it is tasting the water for the first time. The initial data confirmed the crossing, the definitive moment of departure. The gale of solar particles had dropped to almost nothing, a near-perfect calm. In its place, a new population of particles appeared, a hail of high-energy cosmic rays, born in the hearts of ancient exploded stars, a rain that our sun's magnetic bubble, the heliosphere, had always shielded us from. But the most stunning revelation was not about what was gone, but what was there. Our models, our elegant and sophisticated predictions had painted a picture of this medium as a near-perfect vacuum, an emptiness of unimaginable purity. We expected a few stray atoms per cubic meter, a ghostly mist clinging to the bones of the galaxy. Voyager's plasma wave instrument and antenna built to listen to the faint, electrical vibrations of space reported something else entirely. It heard a hum, a persistent low-frequency vibration, a thrumming resonance that told a story of density. The interstellar plasma of this supposed void was substantially thicker, more substantial than almost anyone had predicted. It was not empty. It was a tenuous yet tangible substance. Imagine stepping out of a sealed, air-conditioned building into a humid summer night. You cannot see the moisture, but you feel it on your skin. You feel the weight of it in the air you breathe. This is what Voyager experienced. It left the dry, predictable wind of its home star and entered a thick, vibrating fog of charged particles. This discovery sent shockwaves through the astrophysical community, forcing a fundamental revision of our understanding of the galactic environment. This fog, is not uniform. Like currents in an ocean, it has structure, it has waves, it has dynamic life of its own. Voyager's data showed that this plasma vibrates. It sings in a language of frequency. When a particularly violent explosion on our own sun, a coronal mass ejection sends a shock wave hurtling through the solar system, it eventually reaches the edge of our heliosphere. And though the solar particles themselves are stopped, the pressure wave, the percussive force, rings the interstellar medium like a colossal bell. Voyager, floating in that medium billions of kilometers away, detects the resulting vibrations, the hum, rising in pitch and intensity. It is a staggering realization. Our star, from an incomprehensible distance, is still able to reach out and pluck the strings of the galactic harp, and Voyager is there listening to the chord. We are not as disconnected from the galaxy as we thought. Our stellar neighbourhood is not a quiet suburb. It is a place of constant resonant interaction, and we're hearing its symphony for the very first time through the ears of our silent, distant messenger. This newfound density has profound implications for the very nature of our home in the cosmos. The heliosphere, the protective bubble inflated by our sun's solar wind, is not expanding into a passive vacuum. It is pushing against something with substance, a medium that pushes back. The data Voyager sends us from the outside looking in gives us a perspective we have only ever dreamed of. It allows us to see our solar system not as a collection of planets orbiting a star, but as a single cohesive entity moving through a galactic fluid. This is our ship, and we are finally learning about the sea it sails upon. The interaction is a constant turbulent struggle. The interstellar medium, with its own magnetic fields and particle flows, presses against our heliosphere, compressing it, deforming it. The elegant spherical bubble we often imagine is a fiction. Instead, Voyager's measurements suggest a much more complex and dynamic boundary, a frontier that is frayed porous and roiling with magnetic reconnection events. It is a battlefield where two great domains of magnetism and matter collide, a cosmic shoreline, where the waves of the galaxy break against the shores of our own stellar system. For decades, we have only been able to see this boundary from the inside, like trying to understand the shape of a house, by only ever looking at the interior walls. Now Voyager is standing on the lawn looking back at the entire structure. It is telling us that the wall, this heliopause, is not a static barrier. It is a living, breathing membrane that ripples and shifts in response to the galactic currents. It breathes in and out with the sun's own 11-year cycle of activity. When our star is strong and boisterous, the bubble inflates, pushing the galaxy a little further away. When the sun is quiet, the bubble contracts and the interstellar medium creeps closer. We are living inside something far more fragile, far more interconnected with its environment than we ever knew. Our fate is tied not just to the health of our star, but to the cosmic weather of the local interstellar cloud through which we are currently passing. Voyager's continued journey is a constant real-time report on the state of our defences, a lone watchman on the farthest wall telling us of the forces that gather outside the gate. And then there is the bow wave. Like a ship ploughing through the ocean, our entire solar system, helmed by the sun, is hurtling through the Milky Way at a staggering 230 kilometers per second. This motion, pushing through the newly discovered density of the interstellar medium, should create a monumental structure ahead of us, a bow wave, or more accurately, a bow shock. It is a concept born from fluid dynamics, a theoretical prediction of a vast, turbulent region where the interstellar plasma is violently compressed, heated and deflected around our advancing heliosphere. For generations, this structure has been a ghost, a mathematical certainty that we could never directly observe. We have seen these structures around other distant stars, faint arcs of glowing gas visible to our most powerful telescopes, but our own, the one we are living inside of, has remained invisible, a phantom on our doorstep. Voyager 1, however, is now in the perfect position to change that. Having exited the heliosphere, it is now moving sideways relative to the sun's direction of travel, like a sensor drone being cast off the side of a massive vessel. It is perfectly placed to measure the characteristics of the interstellar medium both before and after it is disturbed by our sun's passage. The data streaming back is painting the first strokes of this invisible masterpiece, by comparing the pristine undisturbed plasma it first encountered with the material it is flying through. Now Voyager is detecting the subtle telltales of this colossal shockwave. It is measuring changes in the magnetic field orientation, seeing the interstellar field lines bunching up and draping around the heliosphere's nose. It is sensing a subtle increase in plasma wave intensity, the crackle and hiss of particles being energized by the collision. These are not theories anymore. They are direct in situ measurements, numbers on a screen that represent the physical reality of our home's violent passage through the galaxy. We are charting the turbulence in our own wake. It's a structure of almost unimaginable scale. If you could see it, this bow wave would stretch across trillions of kilometers of space, a luminous, energetic scar carved into the fabric of the void by our star. It is the signature of our journey, the physical evidence that we are not static but are travelers on a grand galactic odyssey. Voyager is our scout flying just outside the port bow, giving us our first true reading of the cosmic ocean we are navigating. The information resolves long-standing debates. Some models predicted a strong, well-defined bow shock, a sharp and violent wall of plasma. Others suggested that the relative speeds and densities might only create a softer, gentler bow wave, more akin to a boat moving through calm water. Voyager's magnetic field data currently suggests the latter. The interstellar magnetic field appears to be stronger than anticipated, strong enough to divert the plasma flow around our heliosphere more smoothly, preventing the formation of a hard shock. It is a revelation that rewrites textbooks. The universe, it seems, is always more elegant, more complex than our initial assumptions. This isn't just an academic detail. Understanding the nature of this interaction is critical to understanding how our solar system is protected from the harsh radiation of the galaxy. This bow wave is our first line of defense, a kind of cosmic cowcatcher that deflects the most energetic particles and tangled magnetic fields before they even reach the heliosphere itself. It is an integral part of the nested series of shields that ultimately allows life to persist on Earth. By measuring it directly, Voyager is not just satisfying our curiosity, it is conducting the most remote and ambitious home inspection ever attempted. Furthermore, the composition of the interstellar medium revealed by Voyager's cosmic ray subsystem is giving us a direct sample of the raw materials from which stars and planets are born. For all our astronomical prowess, we have always studied this material, remotely analysing the light that passes through it. Voyager is physically touching it. It is counting the atoms, identifying the isotopes of hydrogen, helium, carbon and oxygen that litter the space between stars. This is the stuff of creation, the recycled remnants of long-dead suns, the seedbed for future solar systems. Each particle that strikes its detectors is a tiny messenger from the galactic ecosystem, telling a story of nucleosynthesis in ancient supernova and the slow, patient chemistry of the void. It is cosmic archaeology of the highest order. By analysing this material, we can better understand the chemical evolution of our corner of the Milky Way, and in doing so better, understand the specific mix of ingredients that was available when our own solar system began to coalesce from a similar cloud of gas and dust 4.5 billion years ago. We are in a very real sense tasting the primordial soup from which we emerged. What is perhaps most profound about this new chapter in Voyager's mission is the shift in its purpose. For decades, it was a probe of discovery, an explorer sent to visit known worlds and show them to us for the first time. It was a photographer, a cartographer of our solar system. Now its mission is more subtle and perhaps more significant. It has become a true emissary, a scientific outpost in an alien territory. It is no longer just looking at things, it is experiencing them. The data it sends back is not a picture of a planet, but a reading of an environment. It is the temperature, the pressure, the density, the magnetic field, the very texture of the space that separates the stars. It is the beginning of an entirely new field of exploration interstellar science. We have spent centuries perfecting the art of looking up at the sky, but with Voyager we have finally dipped our finger into it. Every packet of data is a dispatch from a frontier so vast and unknown it beggars the imagination, and with every passing day it sails deeper into that frontier. The faint hum of the interstellar plasma is now the constant soundtrack to its endless voyage. The soft rain of galactic cosmic rays is the weather it endures. The pressure of the interstellar magnetic field is the current it navigates. The probe is teaching us that interstellar space is not an absence, not a void. It is a place, it has properties, it has weather, it has a complex and beautiful physics all its own. This new data is the first page in the travel guide to the Milky Way galaxy, written by a machine that was only supposed to last 5 years. It has outlived its creator's wildest dreams, and in its 5th decade of flight, it is doing the most important work of its life. It is resolving the mysteries of our place in the cosmos not by looking back at the familiar lights of home, but by bravely feeling its way forward into the dark. The climax of its journey was never Jupiter or Saturn. The climax is now. It is this slow, patient and methodical process of translation, turning the subtle physics of the void into the numbers that will define our understanding of the galaxy for generations to come. And it raises a new tantalizing question. If this is the nature of the space just outside our door, what other structures, what other wonders, what other even stranger realities lie waiting for it just over the next cosmic horizon? And so, after months of silence, the conversation resumes. A fragile thread of code stretched taut across 24 billion kilometers of cold dark emptiness reconnects a 47-year-old machine to the world of its makers. That faint whisper, travelling for over 22 hours just to reach us, carries news not from a familiar world but from the great uncharted ocean between the stars. It is a message from the void, a testament from our first emissary to the galaxy. And with its return, we are granted one final chance to stand at the edge of everything we know and listen to the story of a lifetime. This is Voyager 1's epilogue, its final lingering note in the grand symphony of cosmic exploration. To truly grasp its meaning, we must cast our minds back to a time before it was a lonely wanderer. We must remember it as a young explorer bristling with ambition hurled from our world on a pillar of fire and hope. Its primary mission, a breathtakingly audacious grand tour of the outer solar system, was a celestial alignment that occurs only once every 176 years, a gravitational slingshot opportunity to visit the gas giants in a single magnificent voyage. It was a plan born from the boldest dreams of orbital mechanics, a chance to write entire new chapters of planetary science in just a few short years. And Voyager delivered beyond anyone's wildest imagination. It arrived at Jupiter not as a mere visitor, but as a revolutionary. The placid giant of our telescopes erupted into a chaotic, violent world, a roiling cauldron of storms with lightning bolts dwarfing anything on Earth. The Great Red Spot, once a mere curiosity, revealed itself as an anticyclone of unimaginable power, a hurricane so vast it could swallow our planet whole. Voyager showed us that Jupiter was not just a planet. It was a star that failed a seething dynamic system, with its own faint dusty ring and a court of bizarre, captivating moons. It was there in Jupiter's shadow that we received the first true shock of the mission. The probe's cameras swiveled to the small moon, Io expecting to see a cratered, frozen wasteland like our own moon. Instead, they witnessed the impossible, a world tearing itself apart. Plumes of sulfur and ash erupted hundreds of kilometers into space from active volcanoes, painting the surface in hellish shades of yellow, red and black. It was a geological spectacle driven by the immense gravitational tug-of-war between Jupiter and its other moons. A discovery so profound it forced us to rewrite the textbooks on how worlds work. Suddenly, the cold outer solar system was not dead. It was alive with unimaginable fire. Then, flung onward by Jupiter's immense gravity, Voyager set its sights on the jewel of our solar system. It sailed towards Saturn, the ringed wonder, a planet that has captivated human imagination for millennia. What we thought was a simple, elegant set of rings exploded into a structure of staggering complexity. Thousands upon thousands of individual ringlets, composed of countless fragments of shimmering ice and rock, formed a celestial disk of breathtaking intricacy. Voyager saw strange, transient spokes haunting the B-ring dark radial features that appeared and vanished, defying our understanding of orbital physics. It discovered shepherd moons, tiny gravitational tugboats, carving out sharp edges and gaps in the rings, their delicate dance sculpting this magnificent cosmic work of art. Beyond the rings, it gave us our first intimate portrait of Titan, a moon larger than the planet Mercury shrouded in a thick nitrogen-rich orange haze. Here was a world with an atmosphere denser than our own, a place where liquid methane might rain from the sky, carving rivers and filling seas on a surface we could not yet see. It was a tantalizing glimpse of a primordial Earth frozen in time. This was the apex of its planetary mission, the culmination of the Grand Tour. Voyager had unveiled the solar system for what it truly was: not a static collection of orbs, but a vibrant, dynamic, and often violent family of worlds, each with its own story, its own secrets. It had fulfilled its purpose with a flourish, sending back a flood of data that would keep scientists busy for decades. Its mission could have ended there, its legacy secure as the most successful reconnaissance in history. But Voyager's journey was just beginning. Its trajectory, a precise calculation of risk and reward, sent it flying past Saturn and up out of the ecliptic plane, the flat disk where the other planets orbit. It was a path of no return. It would never again encounter another planet. Its new destination was a place we had only ever theorized about: interstellar space. For years it sailed onward, its instruments now tuned to a different reality. The familiar light of the sun, our sun, shrank behind it, diminishing from a brilliant life-giving star to just the brightest point of light in a crowded sky. The mission transformed from one of planetary encounters to a long, patient vigil. It was now a sentry, a lone outpost measuring the solar wind, the constant stream of charged particles blowing outward from our star. This wind carves out a vast protective bubble in the interstellar medium, a magnetic cocoon we call the heliosphere. Everything we had ever known, every planet, every asteroid, every human being exists inside this bubble. Voyager's new goal was to cross its edge to become the first human-made object to ever leave it. Year after year, decade after decade, it flew reporting back on the changing pressures and particle densities as it neared the boundary. The solar wind slowed, piling up against the opposing pressure of the galactic medium, creating a turbulent, frothy frontier known as the termination shock. Voyager punched through it in 2004, entering a bizarre region called the heliosheath. Here the solar wind is hot, dense and chaotic, the last gasp of the sun's influence. For 8 more years it journeyed through this cosmic purgatory, a no man's land between the familiar and the truly unknown. Then, on August 25, 2012, something changed. The instruments registered a sudden dramatic drop in solar particles. Simultaneously, they detected a massive spike in high-energy galactic cosmic rays, particles forged in the hearts of distant exploded stars. The magnetic field, which had been aligned with our Sun, suddenly shifted, reorienting itself to the magnetic field of the Milky Way galaxy itself. The sound of the plasma around the probe measured by its plasma wave instrument changed its tune, its frequency rising to a higher pitch, a new song. The data was unmistakable. After 35 years of travel, Voyager 1 had done it. It had crossed the heliopause. It had left home. For the first time in history, a piece of humanity was sailing on the interstellar sea. It was a moment as profound as any in the history of exploration, a quiet digital achievement that echoed the first steps out of Africa, the first crossings of vast oceans. We had officially become a species that had touched the galaxy beyond our stellar cradle. From that moment on, every byte of data it sent back was a postcard from an unknown country. It told us of the pressures, temperatures and radiation of the space between stars, not from theory or remote observation, but from direct, tangible measurement. It was the first time we could truly feel the galactic winds on our face, and yet we always knew this final heroic chapter of its life would be finite. The source of its power, a small pellet of plutonium-238, has been steadily decaying since the day it was launched. Its heat converted into electricity is the probe's lifeblood, its beating heart. And that heart is slowly, inexorably growing weaker. With each passing year, it generates about 4 fewer watts of power. 4 watts. The energy needed to light a dim refrigerator bulb. That is the agonizingly small margin that engineers on Earth have had to work with. This has forced upon them a series of painful decisions, a slow, calculated farewell. One by one, instruments have been turned off to conserve what little power remains. The camera systems, which gave us those iconic images of Jupiter and Saturn, went dark in 1990, but not before turning back one last time to take the most poignant photograph in our history. The pale blue dot, our entire world a single fragile pixel suspended in a sunbeam. It was Voyager's parting glance, a final look over its shoulder at the home it was leaving forever. Since then, other systems have followed into silence. Heaters for the cosmic ray detector, the gyroscope for the plasma wave antenna. Each shutdown is a small death, a tiny part of its senses going dark, making it a little more deaf, a little more blind to the universe. This recent technical glitch, the long silence and the heroic effort to restore communication was a stark reminder of its mortality. It is an aging explorer at the very edge of its endurance. Soon, perhaps within the next year or 2 or 5, the final command will be sent. A last desperate measure to conserve the last dregs of power for the transmitter alone. Every remaining scientific instrument will be silenced. Its role as an active scientific probe will be over, and then one day the decline will be too great. The power will dip below the minimum threshold needed to operate that transmitter. The carrier signal, that faint, steady tone that has linked it to us for over half a century, will vanish. The great antennas of the Deep Space Network, their giant ears tilted to the heavens, will strain to listen. But there will be only the background hiss of the cosmos. Silence. A silence that will stretch into infinity. And in that moment, Voyager 1 will undergo its final, most profound transformation. It will cease to be a probe. It will cease to be a messenger. It will become a relic. A ghost ship on a sea of space-time coasting on the momentum of its initial launch. Its science mission will be over, but its cultural mission, its true ultimate purpose, will have just begun. Because attached to its side, protected by a shimmering golden aluminum cover, is a testament to the creatures who built it and sent it on its way. The Golden Record. It is perhaps the most ambitious, hopeful, and beautifully naive object we have ever created. It is not a weapon. It is not a claim of territory. It is a greeting card, a 12-inch gold-plated copper disc carrying the sights and sounds of our world. On its cover, a set of elegantly simple diagrams, a cosmic instruction manual showing how to play the record wherein the galaxy it came from, and a basic sketch of the strange bipedal life forms who made it. It is a message in a bottle cast into the greatest of all oceans, and what does this bottle contain? It contains us. It holds the murmur of Earth sounds, the wind, the rain, the crash of surf, the cry of a whale. The sounds of our technology, a train, a tractor, a Saturn V rocket lifting off. The sound of our own biology, a heartbeat, a laugh, the electrical crackle of a human brainwave. It carries the music of our planet, a stunningly diverse playlist that spans cultures and millennia, from Bach and Beethoven to Chuck Berry and Blind Willie Johnson, from Peruvian panpipes to Solomon Island chants. It is an offering of our highest artistic achievements, a single perfect note of human thought and feeling, and it carries our voices. Greetings in 55 different languages, each one a small hopeful prayer sent out into the darkness. From ancient Akkadian to modern Mandarin, the message is the same. Hello from the children of planet Earth. It is a self-portrait of a species painted in light and sound. A species capable of great art and great compassion, yet also one that sends a message of peace, while a recording of a Morse code signal taps out the word per aspera ad astra through hardship to the stars. The record is an honest admission of our complexities, our contradictions, our hopes. We do not know if anyone will ever find it. The odds are infinitesimally small. It is drifting toward no particular star on a journey that will take it 40,000 years just to pass near a star in the constellation Camelopardalis. By then that star will have moved on. Its journey is effectively eternal. But the act of creating it, the act of sending it, is what truly matters. It was an act of profound, unshakable optimism, a declaration that even if our time in the universe is fleeting, our ideas, our music, our curiosity, and our hope are worthy of preservation. A statement that we were here, we were alive, we looked up at the stars and we wondered. Voyager will now drift for an eternity we can scarcely comprehend. It will circle the centre of the Milky Way galaxy once every 225 million years, a silent gravitational partner to the stars. It will outlive its creators, it will outlive our cities, our continents, our languages. It will likely outlive our planet's ability to support life. It will still be sailing through the cold darkness, when our sun swells into a red giant, consuming the inner planets and scorching the Earth into a charred, lifeless cinder. It will become one of the longest surviving artifacts of our existence, a testament etched in plutonium and gold, carrying a whisper of who we were. A lonely monument to a species that dared to reach beyond itself, and that ultimately is its final, most enduring legacy. It is not just a machine of circuits and sensors, it is a piece of the human soul. It represents the most noble part of our nature, that insatiable, unquenchable curiosity that drives us to climb the next mountain, to cross the next ocean, to understand what lies beyond the horizon. Voyager 1 is a physical embodiment of our desire to know. It reminds us that we're not defined by our limitations, but by our relentless effort to overcome them. It proves that a species confined to a single fragile planet can project its senses and its dreams across its solar system and into the galaxy itself. Its journey pushes the very boundaries of what it means to be human, expanding our presence, if not in body, then in spirit, out into the cosmos. As its signal fades forever into the background noise of the universe, it does not leave us with a sense of an ending. It leaves us with a challenge. Its silent, eternal voyage is an inspiration, a call to the future generations of explorers. It is a promise that the human spirit, the same spirit that conceived, built and launched this audacious machine, knows no true bounds. Even as we leave our home behind, we carry its memory with us, etched in gold, a final hopeful greeting to the magnificent, silent and star-filled unknown. The journey is just beginning.